So welcome back to the observatory reports session, where we will continue with the update of the FAST observatory presented by Bill.
Thanks, Stephen. Also, thank you for the conference committee give us this opportunity to present some updates of the FAST telescope. I'm Bin Liu from National Astronomical Observatory, Chinese Academy of Sciences. I give this talk on behalf of Professor Peng Jiang, the director of the FAST telescope. This is the outline. First, I'll give a brief introduction and then operation status, and following by some scientific highlights, and in the end, the upgrade plans. FAST. You all know that the full name is 500-meter aperture spherical radio telescope. It's a national major science and technology infrastructure project funded by the Chinese government. It's constructed and operated by the National Astronomical Observatory. It's the approved investment is 1.15 billion RMB, and the construction period is 5.5 years roughly, and is accomplished in 2016. After that, we come into the commissioning period, which ended in the early 2020. So till now, it has been fully operation by almost 5 years. This is some pictures showing the first one showing the original village where the FAST site is. It's built upon the karst landscape in Guizhou province, which is the southwest China. And the following pictures are taken during the construction period. Now it's like that. The main structure. So there are majorly two main components. One is the dish, and the other is the cabin and the supporting system. So the dish is 500 meters in diameter. The supporting structure consists of 6 towers and receiver cabin. So the cabin can move around spherical in diameter. The diameter of the spherical region is about 200 meters, and you need to control that. The position accuracy request is on the millimeter level, so which is very difficult. And the other difficulty is the active main dish. The illuminated area is 300 meters, and the diameter is 500 meters. So that's why you can steer the telescope to observe different stars in different angle. This shows the details of the main reflector. So the total weight is supported by the ring beam, which is surrounding the main dish. It's the weight of itself is about 5,000. It's more than 5,000 tons. And on that, the cable night is 1,060 tons. So there is also the panel is installed on the cable night, and below the cable night there are down pulling cables. There are like more than 2,000 of the cables. On the ground there are actuators, which there should be an animator, but no, it's not moving. The attenuators works to reshape the spherical surface to make it in parabol and to focus to receive the signal from the universe. above the main dish is a receiver cabin. There are a stored platform to make the receiver accurately localized to have to and to move. The major difference between fast and Arecibo is the active dish, active reflector, and then the other one is the cabin. The cabin is very lightweight. So if I remember correctly, the Arecibo platform is like 1,000 tons of 900. But the fast receiver cabin is only 30 tons. So this is a major difference. But there are three receiver systems. The most important one is the 19-beam receiver, which is developed by our Australian colleagues in CSIRO. It works very smoothly. Among these years, the frequency bandpass is from 1.05 to 1.445 megahertz, and there are other two receivers. One is ultra band receiver from 500 megahertz to 3.3 gigahertz. This ultra wideband receiver is developed for cryogenic cooling system, but unfortunately, there is no enough room on the receiver cabin for the compressor. So currently it's working under room temperature. There's another P-band receiver which covers from 300 to 600 megahertz. These also have a radar backend. Now I'll give some operation status here. The telescope are fully operated by the FAST operation and the development center. This division are fully responsible for the operation and development of FAST. Above this, there are three committees: the scientific committee and time allocation committee and the user committee. They have different function, but they together guide the work of the FAST Operation and Development Center. So there are 5 departments under this in this division: the General Administration Department, the Science Observation and the Data Department. This one normally communicate with the users, call for proposals, and do the service for the data and the data servers. The other 3 are the technical and engineering departments. One structure and mechanical, electronics, and measurement and control. The observation usually takes 3 steps. One, from the top left, is observation management system. Users submit their observation plans, and the telescope operation system deploy their observations, and the data center data are recorded in the data center, and people can log into the data center to download the data, and also can there are lots of computation resources there for the users to reduce their data on site. The blue table shows the plan, the operation plan, which is for each year. So FAST call proposal once per year. So the cycle is 1 year. Each year, the scientific observation time is about 5,000. This is a plan. And there are research and development for engineering time is about 1,000 hours. There are then the schedule maintenance, which is large, but FAST as a giant telescope, they need that. The scientific data acquisition volume per year is more than 10 petabytes. So this is these two figures shows the actual observation times and the data recorded through the past 5 years. On the left side here, I show this is the result for the last year. It's more than 5,400 hours. The total data last year is more than 14 petabytes. There the failure rate for observations is not very large. The data will be published will be open to the public after 1 year protection period. There's two types of proposals or projects. One is the open PI project. FAST call for proposal in the spring. It's normally on the last day of March, and the cycle, the season started after summer in the August the 1st. So this is the last year, a total of 300 proposals were received. Requesting almost 10,000 hours. Only 268 proposals were approved, granting about more than 2,000 hours of observation time. So this on the right side is the total numbers over the 5 years. The open PI project takes about half of the observation time. The other half goes to the K-Science project. At the beginning of the fully operational FAST, there are 6 K-Science projects issued, which was intentionally with their cycle is a 5-year project. So the 6 are here. The first one is a commensal radio astronomy FAST survey craft led by Professor D. Lee, and they are following FAST radio burst survey and the FAST galactic plan pulsar snapshot survey led by Professor Jinlin Han, and others, the CPTA fast timing and the H1 imaging projects. So earlier this year, this 5-year cycle has been ended, and there issues the new 3-year cycle for new KSPs. So there are 8 projects this year. Most of them are the follow-up of the previous projects, but there are also new ones. You can read. I'm not going to read all of them, but the new ones are majorly for H1 mappings of the extragalactic galaxies. As I said, FAST is a giant telescope, so the routine maintenance time is a lot compared to others. So there are geohazard inspections, and for example, the rock, which is unstable, may be dangerous. So they need to spend time on this. They fix and monitoring all the small part of the telescopes. The last thing is the RFI conditions. The major RFI in the fast bandpass is from the satellites. Also, there are occasionally civil flights, radar signals. Within there is no airlines within 30 kilometers of the FAST area, but still it's because FAST is very sensitive, so we can pick up those radars. When there are very strong satellites, the spectral line looks like this. And if there are very strong, very strong satellites going to the fast beam, then the receiver going to be stuttered. So at this time, our operator will shut down the receiver. To avoid this kind of situation, we have a satellite monitoring system, which is actually a database. We calculate and predict this system helps to make the schedule of the observation. Okay, next I'm going to list a little bit of the scientific highlights during the 5 years observation. First, FAST is a pulsar discover machine. During the past 5 years, there are already more than 1,000 new pulsars has been discovered by FAST, which is mainly contributed by these 3 surveys: the GPPS, the CRAFTS, and another globular cluster pulsar survey led by our colleague Pan Zhichen. Among these pulsars, there are many binary systems, which the 2 examples listed here are the most interesting ones. This one has a 53 minutes orbit, which might be the shortest one that we know. And this one may be the first pulsar helium star system. The CPTA, the Chinese pulsar timing array, has give their first data release report, and in their results they report their discovered a gravitational wave background evidence for the HD correlation with a signal noise ratio of 6.6 of 4.6 sigma. If you are interested, you can go to their papers. The fast radio burst is the new frontiers of the radio astronomy. Professor Di Li leads an international collaboration team working on that with FAST. The field of view of FAST is small, but the sensitivity makes it very powerful to study repeaters. So these I'm not going into the details, but these are all the highlights papers they found, they published. So if you are interested, you can go over that. The other major topic for FAST is the extragalactic H1 galaxies. There is a survey called FASH, which has been detected more than 40,000 galaxies. It's still ongoing project, and in the end, they will give the largest extragalactic H1 catalog. And on the right side is an example that shows the power, the capability of the FAST at the single dish telescope. So it's revealed a 2 million light year diffuse neutral hydrogen gas structure, which is the largest ever detected. In the end, I'll shortly give the upgrade plans. The first one is the phased array feed. We have already done a first generation prototype. This is here, and there listed some parameters, and there is also an ongoing project. So we're gonna develop a fully functional path system. This is the specs we are going to accomplish. As I said, there is no enough room for more receivers in the cabin right now. So there is a plan to update the receiver cabin with a lighter weight and a larger platform that's for more receivers. In the end, FAST at a single dish telescope has accomplished a lot, but still the resolution of it is limited compared to other arrays. So there is a plan to build a fast core array, which is to build 64 new 40-meter telescopes around the 30-kilometer range from FAST. So here we have already built up 2 telescopes. This is the first one, and the result came out. So this is a fringe of the visibility between FAST and the first element, and this is a pulsar observation with the telescope itself. And this is already there, and there are 2 coming later this year. Hopefully we're gonna accomplish this goal in the future. I'll stop here. That's about it. So if you have any questions or interest in collaborations or suggestions, please send me an email or send this is an email of the FAST office, and this is my email. So that's it. Thank you.
Any short questions? Anything else?
Very interesting. So you can slide about the different departments that you have.
Yes. This one?
Yes. Where is the software?
Sorry?
The software team.
The software team.
Yes.
The backend and the software is in this department. So we have a receiver team which there are people working for the front end and the back end and the softwares. Also, it depends. So which software? You mean the receiver or the control system? Or so on each one. So the control system is developed by this department. The receiver system, the control of the receiver is in this department. So
The engineering departments, you don't have a separated software department.
yeah, it's divided by the function, not the field.
Thank you.
Mm-hmm.
Thank you. So let's thank again. But move on to next speaker. Before giving 2 questions, technically. Let's start with the first one. He will be he alluded to in the other presentation the wideband sensitivity upgrade. And this hope he will give us an overview of this wideband sensitivity upgrades.
Okay, thank you. You're the brave ones. You will be stuck with me for 40 minutes. So the first one is indeed about the a major upgrade that will take place, and have put just a few people here, but of course it's a huge collaboration. And I'm going to give you an overview of the preliminary system design of WSU. So WSU in a nutshell, it's a major, very ambitious upgrade that will dramatically enhance ALMA's coverage, spectral coverage and observational efficiency. That's the highlight. And how will this happen? Because first of all, we're going to increase our IF bandwidth. Surely it's going to be 2 times more, hopefully 4 times more. So what you see in this plot, you see the different bands, band 1 to 10. They have different IF bandwidth, depending on whether 2-sideband or double sideband detectors, they have different IF bandwidth. Some of them are already available for the 2 times. So band 2, for example, has which already been implemented and installed in our receivers, has an IF that provides 32 GHz, but other bands not. So gradually, we're going to increase the IF starting band 6 and 8 to 16 or 32 GHz. About the correlated bandwidth. So currently, with ALMA, if you want to go to specific velocity, you have to sacrifice your spectral resolution. And as an example, I have put here a central frequency of 240 GHz in band 6. And if you want to go to 0.04 kilometers per second, your correlated bandwidth is 0.2 GHz. If you go to higher velocities, 1.2 kilometers per second, then your bandwidth becomes 7.5 GHz. Okay, you can't have both. Well, if you go WSU, you're going to have both. You're going to have 0.1 kilometers per second, and you'll have the full bandwidth coverage, as you can see in this graph. There's no reason to think about how I'm going to do my tunings to get one of the two. And this is how WSU gives enhancements on the correlated bandwidth for different bands. And the advantage is impressive if you go to the high spectral resolution, which is the bars in orange. The impact is not that high if you go to low spectral resolution, but WSU will enhance significantly our capabilities, especially in the lower bands, band 1 and band 2. What does this mean? We're going to have a very, very significant improvement in our observing speed, okay? So for the continuum, we're going to have about 5 times if we go to 2 times IF bandwidth, and up to 9.6 to 10 times if we go to 4 times the bandwidth. We're going to be taking data faster, we're going to be more efficient, and of course, for spectral lines, we're going to have a major advantage as well, because your IF bandwidth will be much larger, okay? This also means that we're going to have improvement in our efficiency because we're going to have improved receiver temperatures, improved digital efficiency, and the bandwidth, of course, is going to be larger, which means also that spectral scans observations will have further increase in the speed because we're going to have a larger correlated bandwidth. To put things into context and connecting my previous presentation, ALMA competes with itself. So it's part of our integral operations plan to continue developing ALMA. There's a specific budget allocated per year for development projects, which is being used to update the hardware, to update the software, to do studies which enable better performance from the operational perspective. Okay. Of course, the development program is driven by science, which of course is the ultimate goal of ALMA, because we want to enhance the capability that ALMA offers the scientific community. The fund is coming from the executives. They have their development program budget, and we're in charge of installing everything at the observatory, and in coordination, of course, with the respective teams at the regions. So regarding W specifically, we have a document called the ALMA 2030 Development Roadmap, which gave the vision of the ALMA development program for the following decade. And it's clearly stated in the ALMA development roadmap that ALMA, within the first 5 years since it started operating, it reached all scientific goals. All 5 scientific goals were reached within 5 years of operations, right? So I had to set new science goals, and this is what drives the ALMA 2030 development roadmap. New capabilities that were able to study even more the origin of galaxies, the origin of chemical complexity, and the origin of planets. In that document, it's clearly stated that priority, there are several priorities, but number one is to broaden the IF bandwidth by at least a factor of 2. And of course, this means we have to upgrade the associated electronics and the correlator. This is a complex slide, but in principle, when you go and update your IF bandwidth, you have to update the whole signal chain. To oversimplify, the only thing that will not change is the antenna dishes. Everything else is impacted. The receivers, of course, have to be upgraded for 2 times or 4 times the IF bandwidth. And of course, if you upgrade the receiver, the analog part, you have to update the backend, the digital part. So all the data transmission system, the digitizers have to be upgraded as well. And then you have to think about the correlator. So our correlator is, the 2 correlators, one has been commissioned, is at 5,000 meters in the AOS technical building that we see here. That will no longer be the case. The new correlator will be installed at 3,000 meters at the operation support facility. So entering that building at 3,000 meters on the left side, we'll have the control room. That huge room now will be accommodated to host the correlator there. So our new correlator has to be hosted in a room which is not supposed to be one for a correlator. So that's a major project itself, the OSF correlator room. And since you put the correlator at 3,000 meters, you need optical fibers. So you have to do all the micro trenching to be able to connect the antennas at the AOS at 5,000 meters, 16 kilometer baseline, to 3,000 meters, which is 40, 50, 60 kilometers down. Okay, another project which is very challenging, do a trench and put those optical fibers that will connect antennas to the correlator at 3,000 meters. And of course, we're going to have another correlator there. So the total path spectrometer, the TPGS, will also be hosted there in the USF correlator room. And of course, you have to think about the associated computer infrastructure, both of software and IT. Optical fibers is one of them. There are many more challenges. This is a huge project. It's extremely expensive, very challenging. And we share the challenges and concerns that Luis presented for SKA. So this can only be done in a staged approach. Okay, different phases, different milestones. We call them milestone 1 to 5. Milestone 1 is the minimum viable product. I will call it like this in a simplified way. The minimum things we can provide the astronomical community with 2 times the bandwidth and make sure that we can provide the scientific abilities we're providing now. M2 means that we'll finish with the assembly, integration, and verification AIV of all antennas. Not all antennas will be retrofitted when milestone 1 starts. Most of them will, but probably not all. The goal is that when milestone 1 starts, we provide the same sensitivity as we're providing now with the 66 antennas, 50 antennas for the baseline correlator. But since we're going to be much more efficient, this can be done with 36 antennas to about 40. Milestone 3, we finish the commissioning of all the observing modes. All observing modes will not be offered at once. That will be done gradually. And then milestone 4 will finish what we call the end of data processing transition. So we need a new software to process the data, plus the associated infrastructure. Our software is not capable of dealing with so many data, and we have to rewrite our software, mainly for the pipeline and custom pipeline. And milestone 5, deliver all top scientific priorities we want to offer the community with 4 times for the bandwidth. So the preliminary system design provides a design of the system when all milestones have been completed and considering an IF bandwidth of 4 times the current bandwidth. Okay, so it's a system level design. So we're providing in a document a description of all the major components, the operations, the infrastructure of computing, including software and hardware, okay, and the signal chain. And the system design will evolve as a function of time because it needs to mature. Okay. And we have system technical requirements which are very well defined, and our system design has to match those system technical requirements. So I was coordinating the system design description, and we had the challenge at the beginning to put all these things together. And then we realized that actually we had no single document that was describing the current system design. Funny discovery after 10 years of operations. Well, it happens. It was a nice challenge. So after quite a lot of thinking, took me about 2 weeks, and discussing with colleagues, we came with this idea of presenting the system as different layers. You start the operations. And in case of ALMA, we have, of course, to start with the proposal submission project preparation. You continue with data acquisition. Then you have to calibrate your data, and you have different science observing strategies, as we call them. Then you have to process the data offline into quality assurance. And at the end, you deliver the data community. And of course, the PIs and the community has to have access to the data. So this is the process at a very high level. What you do then is you define different layers that sustain this operation. And you start, of course, with the signal chain, right? But then you have to have other layers. And one of them is the IT infrastructure. Another layer is the software infrastructure. And then what we added in the case of the system design, non-functional constraints. So this is the way we visualize our system design. And if you look at our document, you will see that's exactly chapters that completely clearly separated from one to another, but having this vision. How do you describe a system which is so complex and you have so much interconnectivity, right? We came up with this scheme, and this is what you will see as said in our system design description document, SDD. Obviously, I'm not going to go into the details. You can find it in documents, but the highlight in our case is when we did our assessment, the processes will not change significantly. Fundamentally, nothing changes. The impact is small in most cases, but we have significant changes in our quality assurance. The data processing quality assurance is significantly impacted because we're going to have many, many more data. That's fundamentally what happens. Okay, so you have to do things in a different way. For example, now you run your pipeline, you have a block of data. For any reason, the pipeline fails, you start from zero. You cannot do that if you have data sets which is 50 times more. Simply, you cannot do that. You cannot waste resources. You don't have so much processing power. You have to be smart enough to say, my pipeline failed at step X, I resume from step X, for example, right? Input output is a major issue. So you have to think about you do things because you need to optimize. You don't have the luxury of not optimizing any longer when you go to this level of complexity. If you think about the signal chain, as I mentioned before, of course, we're going to have wideband receivers. Band 2 is offering already 32 GHz bandwidth. We're going to have new versions of band 6, 7, and band 8. Funding is still to be considered for band 7. And they will provide IF bandwidth 32 GHz per polarization and improved noise performance. And if you think about our new correlator, which is called ATAC, the Advanced Technology ALMA correlator, and the TPGS, the Total Power GPU spectrometer, they will allow to process 32 GHz per polarization at a very high native resolution, 30.5 kilohertz, and going to have 2.5 million of channels. So significant many more channels compared to what we have now. That's why we'll be able not to sacrifice spectral resolution for high velocity. Okay. We're going to have much higher digital efficiency and higher bit depths. We're going to go from 3 bits to 6 bits. That's a huge improvement as far as our efficiency is concerned, and including digitizers and correlator, and again, sensitivity of factor 1.23. in addition to any gains that come from lower noise amplifiers in new receivers. What you see in this table, it's an increase factor compared to what we have now. The peak data rate's going to be 63 times higher. The raw data volume combining the three arrays, we have the 12-meter antennas, we have the 7-meter total power, is going to be 50 times more raw data compared to what we have now. And the product volume, so when you process the data, you make your spectral cubes, your images, is going to be more than 100 times more. And then total data volume, about 90 times more. And about the processing performance, we have a very big cluster, 50 nodes, 256 gigabytes of RAM each. I don't recall, 16 cores per node or 32. That's not going to be enough. We have to improve by 130 our performance to be able to increase by 130 our performance to be able to cope with the data we'll be receiving. Okay. And if we look at from the software layer perspective, there is of course an impact. In most cases, it's not significant. We know that we can cope with them, but there is one specific part of the software that will sustain a specific process that has declared, I cannot cope with WSU, full stop. And that's the CASA plus pipeline combination. Is anybody using CASA? Right. Do you love CASA? It's challenging. CASA works fine, but it will not be able to work with these datasets. It's a very, very old software. So we're aware of the challenge. So and it's much more than just CASA and pipeline. It's the whole infrastructure that deals with the data, that manages the processing cluster, that takes smart decisions about when data fail, et cetera, et cetera. So it's going to be a new ecosystem, which we call RAD-PS ALMA. It's radar astronomy data processing software. It's going to be dash VLA, GVLA dash ALMA. There are two ones, like CASA is providing software for different observatories. RAD-PS ALMA will do the same. There's going to be one for ALMA, another one for the GVLA, and will provide more efficient parallel data processing, optimized computer resource allocation, and improved fault tolerance, which is very, very important for us because we cannot just reprocess the data from scratch. Just a short notice about non-functional design constraints. We're considering, of course, project quality and standards, safety, electrical and electromagnetic compatibility, system environment, system configuration, and RAM. So what's the WSU current status? So we passed, and we're very proud about this, our preliminary design review. We had an external panel that evaluated our maturity at the beginning of July in Charlottesville. 13 members came and we spent 3 days with them discussing about presenting our plan. They were very, very pleased with what they saw. So we're happy to go to the next phase and actually looking forward to receive their report. It should have been available, but it will be in the following days probably. And what's coming next? We have already several projects in place, and the OSF collator room passed its CDR in June 2025 and will proceed with the procurement and construction phase. So that's great news because it's very, very challenging. The OSF collator room is going to be a huge room that has to be accommodated for the collator, and air conditioning and everything, all the construction work. You know how the control room looked. It's a very expensive project on its own, including all micro trenching, et cetera, et cetera. All these are expensive projects, very challenging if you work at 5,000 meters. And of course, it's much more than just machines. You have to have people doing all the work. Okay. So just very selective, biased Gantt chart with very few points here. The ATAC CDR happened just what is here? yes, the attack CDR is going to happen the Q4 2025, so not the one for the self correlator room. Now the correlator room is okay. Now have the correlator itself has to pass its CDR. At the end of the year, we're going to have a software PDR at the end of Q1 2026, end of March 2026. Software is a very, very important component, of course, of the project. And if all goes well, we're going to have the first components of the new correlator arriving around July, August 2027. So just less than 2 years from now. So in between, other PDRs will take place, different bands, DTS, etc., etc. And I'm going to talk about our AAVC plan in the following presentation because it's very, very important to start preparing that as well. So I'm going to finish with this slide. A lot of exciting science with WSU. What you see here is a graph coming from the MAPS large program. And what you see in these black bars there is the different tunings that ALMA is providing this moment to be able to observe specific spectral lines. And actually, with WSU, we'll just do it. We will have all that part in one observation. So having X, we just with one observation, we'll have all that covered for 2 times in the blue and 4 times in the orange. So a lot of exciting science to happen. And I think that's, yes, thank you for your attention.
Thank you, George. So, as George was giving messages, it's also about WSU. And also, if you have time, I think we can move on straight to the next stage.
Sure.
And we take all the questions here.
Yeah, absolutely. Okay. So, disclaimer, this is a preliminary plan. Don't look at the dates. What's important here is the concepts. We spent about 1.5 years thinking about the AAVC plan and know it's challenging, and I'll explain why. A lot of people have been contributing this work. We're grateful for all the work that they have done. So you see their names there. We have had a lot of fun thinking about the plan. And I will start with the definition, of course, of AAVC, right? So it's a process that will ensure the seamless deployment and operational readiness of ALMA WSU system. It encompasses the installation of new and fast components, subsystems and processes, and their integration, which is fundamental, the integration into the WSU system. Okay, this is what, okay, again. System definition. What's a system to start with? It's the ensemble of hardware, software, and compute infrastructure, and science operation processes which work together as a system to deliver high-quality scientific data products to the astronomical community. And as explained before, we expect we have 2 times or 4 times high bandwidth with WSU system. Why this definition is important? Because when we think about the integration, we think about integrating hardware, software, and the operational process to be able to enable ALMA in the WSU era. You cannot just think about one. You have to think about all of them. The different layers that I mentioned before. Software, hardware, and processes. Once you have installed, once you have integrated, then you have to verify. You will have specific requirements against which you have to verify that your system works. And you have, of course, technical requirements, and you have scientific requirements. And then you have to ensure the implementation of targeted software and hardware refinements, because you don't have data that will reveal problems, to be able to reach your goal, which of course to enable PA science and full operations with WSU. So we're having a huge challenge here, and failure is not an option. we will be doing the upgrade while operating. We cannot just close the observatory for about 3.5 years and do what we want to do. It's just not possible. So we have presented a plan that will allow to gradually retrofit the antennas, integrate, verify, and at the same time operate the telescope as long as this phase continues. Okay. So this is what we call parallel deployment concept, and that's why meticulous planning is fundamental. There's a major advantage if you follow this approach is you have a fallback option. If anything goes wrong, if there are any delays, you take away pressure from the AIVC team. You go back and you continue taking science data. You keep the community happy while you try to troubleshoot. Not all components will come together. We talked about the receivers, data transmission system, digitizers, fiber optics, etc., etc. You will not have them on day one. They will come gradually. And if when you have started the process, you identified problems, you can just switch to science while you troubleshoot. What you see here, I will not go into the details. This is our WCU block diagram, but the most important thing is that you have your receiver, you see, yes, you have the different front ends, and then you have a parallel deployment splitter that will split the signal from the front ends to the different paths. And then you can choose to continue with the legacy backend, or you go to the new system. So you choose which one of the two will be using, and then you go from front end, digitizer, legacy, or the new system, and then you decide how you continue, of course, right? We're going to have new digitizers, fiber optics that will connect to the new correlator, which is going to be at the OSF, not any longer at the OS. So you will be able to follow the end-to-end signal chain down to your archive by choosing one of the two. You can continue taking new data or data with WSU by using the splitter of the parallel deployment, which will be in the front end. Okay. So the process of AAV first. What I have here is just a screenshot of our work breakdown structure that shows different packages we're going to use to do the AAV. And of course, you have to prepare your infrastructure. For example, micro trenching, putting new optical fibers is part of our infrastructure. Accommodating the new OSF converter room is part of the infrastructure. You have to prepare your infrastructure. And then what you have to do, you have to prepare what they call previous acceptance on site. So the LRUs, the different components, the line replaceable units will start coming in ships, in batches. And then you have to accept them, do quality assurance, accept them, and then start retrofitting the antennas gradually. Okay. You have to install them on all 66 antennas. Then you have to calibrate, take data, calibrate, check that everything is fine, and verify gradually that you have integrated specific components into larger system and gradually operating together, thinking about individual components, antenna level, correlator, etc., etc. And then you go from smaller level to telescope level. And then I will not go into the details of the stages, but what you're doing actually, what you receive at the OSF, your components, you do your checks there, and then gradually you start retrofitting. We're going to do basically retrofit at the OSF at 3,000 meters for just 4 array elements. You want to reach amplitude closure. So we're going to do first retrofit on a single antenna, another one, then get fringes, Of course, you need to get fringes, you need the new correlator to enable it. And so this has to be done in a very careful way. And then you have phase closure and closure. You do some checks. You check that your basic system with just 4 antennas work properly. But at the same time, you start retrofitting antennas at 5,000 meters. So you try to enable partially things happening at the AOS. And then you will do some reviews, basic checks for commissioning. And if things are fine, you go to the AOS at full speed and you retrofit on a continuous and steady pace, and you integrate more antennas and you commission taking more data with more array elements. That's the whole. In between, you have gate reviews to make sure that everything is fine because before you go to the next step. But you have to somehow speed up the process. That's why some things have to happen in parallel. The disclaimer is mainly for this graph, so don't think about the data themselves. But what we're planning to do is, at the beginning, we're going to spend quite some time on just a few elements. Once we feel more confident, then, and we will write procedures, the engineers have to, and technicians will have to get involved in that. And then once we feel confident with this, please, but the photos, please, just only for reference, this is a disclaimer I said, okay, that once we feel comfortable, we go to the AOS and we follow a more aggressive retrofit scheme, okay? But we're going to spend quite some time at the OSF when it's more comfortable to do any checks and improvements from the engineering perspective as well, okay? If everything goes well, we're going to have a retrofit cadence of 16 days. And of course, you don't only need to retrofit, but you have to integrate the antennas. This means a lot of time taking data on the sky. You have to do some spectral checks, make sure that your data are being sent properly, the bands don't have pure signal, etc., etc. So if all goes well, we expect to finish within 3.5 years. We have considered margins in our learning curves, margins about the commissioning process because we have to retake data, margins about learning how to do things, etc., etc. And of course, it's not only the antennas, it's the whole system, as I mentioned before, the system, the correlator, TPGS, the software, the control system, the procedures, having the right people to do the work at 5,000 meters, etc., etc. A challenge that we'll be having as well, on top of everything else, is that we have what we call critical number of antennas that we need to have available to take scientific data. So if you think about a 12-meter array, we have 50 antennas. If you go below 41 antennas, you stop taking data. Full stop. Your sensitivity is too low, so you don't take data. So what will happen at some point, you will have retrofitted main antenna elements. So you cannot continue taking data with the old system. You have to take data with the new system. So at some point, we'll not be taking data in parallel. We'll go to interleaved mode. The beginning, we'll only retrofit 4 antennas, taking 4 antennas away from 50, it's 46, it's okay. Some will have failures, but will not go below the critical. But at some point, you will go below the critical. So what we'll be doing then, we'll stop taking data, PA science data, we'll not take commissioning data. Then we have to go to PA science commissioning. That's what we call interleaved. There's not going to be longer in parallel, but we have to move on with the ABC plan. So we'll have to stop PA science and take data, process them, assess the situation, and then move forward. And a few things about the commissioning. Of course, our goal is to commission, and the goal of commission to deliver a fully functional interferometer capable of supporting WSB-enabled PA science. And during the commissioning phase, the retrofit elements will be extensively tested and integrated to achieve the required technical and scientific performance. This is a list of all the output, procedures, observing modes that have to be properly validated, workflows, how the data move, different life cycles, states, as we call them, make sure that everything is happening as expected, performance reports, gate reviews, where we'll assess the situation, and error handling. So when we face problems, how we're going to deal with the problems. We now have a Jira system which is very robust, very well used. Or it will be challenging to see if a problem is because of the new signal chain or the legacy signal chain, because you don't have components in parallel, both of them coexisting in the front ends and the rest of the signal chain. So we have to think about how we're going to deal with all this. And of course, we need to have test data, both for the observatory science facility and commission data that will be used to assess the situation, and of course, science verification data later to enable, before enable PA science observations to the community. There's another group which is called TWO, Transition WSG Operations, with whom we have to coexist, because things will not happen, it's not black and white. It's not that one day you declare we are done and the other team starts to operate. The operation of the observatory have to coexist with us. We have to coordinate together what will be happening, who hands over to whom what, when, and this has to be done in a combined way, so can agree how we transition smoothly when we say that commission is done, we're ready to go to the first observing cycle with WSU. There's going to be some flexibility regarding the observer cycles. So I mentioned before, if you remember, that we start a new observing cycle every October 1st and it lasts 1 year. We have explored the possibility, and actually this is what was mentioned, this was not here, to extend our observing cycle during the AVC phase for 2 years. If we're not ready to start, we'll give 3 months or 6 months extension between a go and no go. So it's going to be an iterative process with WSG operations, because we cannot just wait for 1 more year. We might be ready before the start operations with PA science. This will be assessed with the WSG operation teams. The other thing which is also challenging, of course, is long baselines. You don't want to start with the most challenging observing modes, which is long baselines, high frequencies, 15-kilometer baselines. You want to start with something simpler, but of course, starting simpler you don't want at the same time block any PA science which related to long baselines. So this has to be combined, considering when we will be ready to move to the next phase and offer PA science. We cannot just say for 3 years we're doing commissioning, we don't take long baseline data. You want to offer the community, so this has to be coordinated as well with the traditional WSU operations as well. So our assumptions and principles, that software and hardware will be ready when needed to be properly tested, integrated. And of course, we're going to follow a stage approach. This will be done gradually. This will be carried out with all available R elements. The traditional WSG operations understands that for us, it's a very important element to have as many retrofit R elements as possible to take the best possible quality data, high signal to noise, and of course, also test the software itself. Okay, it's very important if check for scalability issues. Priority will be given over legacy science. We should not, of course, forget that we have enough experience. Okay, many of us have been involved in the construction of ALMA, and we have more than 10 years of operating observatory. So we have a lot of experience in both operations and construction and AIVC. I was part of the AV team in the construction phase in 2011. So all of us who have been involved in this process will be contributing to do things in a very organized way and very efficient as well. We also expect to have higher failure rates at the beginning of commissioning. Okay. And we'll be following standard practices, including health checks and same periodic stress tests of the whole system. Okay. Planning. That's our core philosophy. It's very, very important. It's going to be very complex. Well, I can give an example. When I was AAV, we had to do a lot of tests on each antenna. And by definition, when we delivered the last antenna, our team dissolved. It was a project, right? But the challenge would be who's going to do the work we had been doing if we want to check any procedure. So somebody had to write thousands of lines of procedures that could be given to anybody, that could be dummy proof, really anybody. Go, you check the procedure, you follow them, and you are able to execute the test that our team has been doing for 3-4 years. So we had to ask volunteers to come and check the procedures. I was in charge of writing them on Wiki at that time. And we're asking people, volunteer, come, sit with me. Can you do the test without me helping you? We have to become at that level of, efficient and sure that things will be documented properly and the reviews will happen as they have to happen. And this means training, a lot of training, so that we can get as much support as we can from colleagues and gradually commission different observing modes. I have covered most of this. Last point, it's integration. We're going to integrate, starting from the basic components, LRUs, a receiver, digitizer coming, and then what does this mean for the antenna? The antenna itself, is it behaving properly? Is it pointing the focus different tests? Then you put two antennas, fringes, then you have circle dependence with the correlator. You cannot, verify the correct antennas. You cannot verify the antennas without correlator. We have to gradually integrate everything so we can move forward with more complex tests. 3 antennas, 4 antennas, add the OSF, then OSF, optical fibers from the antennas at the AOS, connect the correlator, the OSF, so on and so forth. So it's going to be a challenging process. We have thought about it. We're going to improvements, but we have thought about all these aspects, and the system PDR has given us confidence that we know what we're doing. Okay. System integration campaign, same concept, and that's a summary. I will finish here. Thanks for your attention. These are the most important points that we reviewed, and I'm going to take questions. Thank you.
Thank you. So it's very nice session thoughts. Are there any questions? Yes, that's all I do.
I'm not sure how best to put this question, so bear with me if it first doesn't make sense. I'm trying to figure out the difference between the commitment, if you will, to double the IF bandwidth and the goal to quadruple it. Is the point that all of the hardware will definitely be capable of handling 4 times the bandwidth, but that the computing and software might end up somewhere in between, or where does the slack occur?
Money.
It's
It's a budget. It's a budget.
So
yes.
The hardware itself is not capable of delivering 4 times the bandwidth.
It might be that there will be delays in the project that will consume the money available.
Yeah.
Marching army.
Sure.
So it's the risk. Okay, then the risk analysis is extremely important to be able to assess the risks and what will be the possible impact. So have a very detailed risk register, and are very careful about all the risks. And of course, having a similar scheme as SKA, there are things you cannot control. What's happening in the regions, because they are leading the development projects, is don't control. But the main concern is not the hardware software itself, is the delivery. It's the programmatic aspects, what's the challenging part.
I guess carrying on from that, I guess the doubling the bandwidth comes from the 2 sidebands, and the other double comes from doubling the IF bandwidth.
Yes.
If you went back to 2 times the bandwidth, would you reduce the IF bandwidth or go back to a single sideband?
The bandwidth itself will allow you to get the 2 times. But I mean, the idea is that the receivers are capable of providing 4 times on their own. So that's it has not been confirmed yet for all bands, but they're being designed for 4 times bandwidth. And then all the signal chain follows that assumption. Okay.
So if you did drop back to 2 times the bandwidth, it would be
yes.
Subsequent.
Yes.
And you could choose.
Yes, exactly. Yeah.
Also, further question. I'm just wondering why you're moving the car later. Is that because of the parallel deployment?
No, because it's much simpler to maintain and do all the, at the 3,000 meters. Yeah. 5,000 meters has a lot of complications, and also you don't easily find people who have expertise and work at 5,000 meters, so it's much more simple. You have a major investment at the beginning. The cooling system, for example, is very challenging, but once you have done that investment, much simpler to do everything at 3,000 meters. It's really literally next door. Literally next door.
Another quick one. What does a stress test of the whole system look like?
Having all the taking data with as many antennas as possible and seeing if the software is able to cope with that. The data processing software will not be RADPS ALMA will not be available when you start commissioning, or AAV. It will become available in about 10 years from now. So what we're going to do is we're going to do in the meantime an update of the pipeline so that it can process the data, starting the calibration. So we have to give to the pipeline team enough data and check whether they can process the data at a reasonable amount of time, monitor input-output performance, and transferring the data. Of course, we have updated our switches, Ethernet switches, 100 Gbps, data transfers, how long they will take, all the OSF data buffers, so we have enough infrastructure of OSF that absorbs the data and then sends them to Santiago. All this has to be stressed and see if we can, the upgrades that we have done, including infrastructure, IT, and software, can provide a smooth transfer of the data in just the archive and the replication of the ARCs. So the whole signal chain.
Okay, so one final question is was one question.
When you mentioned the legacy thing and the new thing, you can switch back. But for the backend part, I think it looks like a completely independent system, so it's easy to swap back. But if something wrong with the receiver, you cannot easily swap back to the new receiver to old receiver. What you're going to do?
The receivers will not going to be. The receivers will be upgraded, okay. But of course, they have to go through CDR and manufacturer readiness review before they arrive. So we're going to have a few non-production models that we're going to check. But of course, we expect that when it pass all the reviews and they arrive, there are no problems with them. Okay. One possibility is that there's a delay with the production units, for example. Or we find, let's say, interference that have not been identified before, but something that we have to deal with later. But we hope that when the receivers pass their CDR and MRR, they arrive with no problems. Of course, integrating is the challenge. So we're not concerned about problems with the receivers themselves, but maybe the integration might show us some problems.
Just for the curiosity. Early days of the 2010, the AIV and CSV commission science verification, there were two teams independently working, but this time it's going to one. Just because I was a CSV member. So
yes, I know. Actually, it's not going to be one team. It's going to be different teams. We just put them together. Actually, as the science will be even, it's not going to be CSV. It's going to be commissioning team. AAV commissioning and science verification are going to be split. They are different things. They have different roles. Okay, commission and science verification, it's not the same thing. So we have learned from our previous history, so we're going to think differently. Good to see you.
Thank you again.
Thank you.
Thank you for attending the session and enjoy the rest of the day.
Now you're tired. Thank you for giving the opportunity to give this talk. Appreciate it. Thank you for the opportunity.
Thank you, of course.
I want to get the feedback and have some opportunities to exchange some notes about how to validate.